based on these considerations that I've just kind of gone through, we can try to break down the HHV efficiency into components that represent different things that we can either engineer or we're stuck with. And I think it's a useful way to think about it. So if we just think about how the HHV efficiency is defined, this is the electrical work that we're producing divided by our fuel flow times delta H0 of reaction at 25 degrees C. And the reason it's done that way is usually when people are talking about the higher heating value, it's not at a particular temperature. It's just taking the value at 25 C, which may or may not be the same as the one that's relevant to the operation of the fuel cell. Obviously, if you're in a PEM, it's very close to that. But if you're talking about a solid oxide fuel cell, which might be up at 1,000 Kelvin, then delta H may not be the same. So we can factor that out sort of immediately. If I take this, just take delta H of reaction at temperature T, divide by delta H of reaction at temperature T, just as a unit conversion, that puts us on a basis that is related to the thermoneutral voltage. Breaking this down further, this is going to be N dot fuel times the fuel utilization times NF times V cell. That's the electrical work. And then I'm dividing that by N dot fuel times delta H of reaction at temperature T. And then I'm going to put in this ratio of delta H reaction, temperature T divided by delta H0 of reaction at temperature at 25. And at this point, the other thing I can do is recognize the delta H of reaction. This is equal to the thermoneutral voltage. Put the NF down there. These are canceling. So these negative signs cancel as well. And fuel is canceling. NF's canceled too. Now I'm going to also multiply by V equilibrium divided by V equilibrium. So we're going to have the fuel utilization. We're going to have V cell divided by okay. I think that's all the factors that we end up with. So if we break it down, the efficiency, what makes up the higher heating value efficiency? It's saying there are basically four components to this. There is the fuel utilization. How much of the fuel actually gets consumed and turned to electrical work. There's sort of a operational efficiency of the cell. And how close is that cell operating to equilibrium? If it's farther away from equilibrium, the less efficient the system will be. There's also a component that has to do with the inherent ability of turning this reaction into work versus heat. And that's what we're talking about with the thermal neutral voltage. Because there's a difference between delta H and delta G, there's an inherent limit to how much work we can produce. In some cases, we have to produce a certain percentage of heat. And since we're using as our denominator the heating value of the fuel, we're asking how much of that heating value must go to heat, just even if we do everything perfectly reversible. So this kind of is like a thermodynamic limit. And then finally, we have this last term, which may or may not be important, but it's basically a baseline shift in our basis of the comparison. From 25C to whatever temperature we're operating our fuel cell at. Right? In a sense, it's like a trivial quantity or an arbitrary quantity, because whatever delta H and delta G are doing as a function of temperature, that'll impact how relevant the delta H of reaction at 25C is to our problem, I guess is the way I would put it. It's not really an efficiency in a traditional sense. It just represents a baseline shift. So if we think about like, what do we control as engineers? I think it's important. This is the part that I think is like important to understand, maybe more than anything. The thermodynamic limit of how much work we can produce versus the fuel value, there's not much we can do about this, right? Nor can we do much about the baseline shift. It's the other two that we can actually do something about as engineers. So how much fuel we use, what percentage of the fuel actually gets consumed electrochemically, and how efficiently we convert that fuel relative to the equilibrium potential, that's where we can actually make a difference in terms of how we design the cell, how we operate the cell. So this is the part that's subject to engineerability. Is that a word? Engineerability. I'm not sure that's a word, but I'm going to use it anyway. So this is the part where we're gonna focus on the most.
So on the first line, I just want to make sure that this is correct. You multiply it by delta H of reaction over delta H of reaction. Is one of those supposed to be standard enthalpy of reaction?
So all I'm doing here is I'm multiplying by 1 in order to create, to group those terms together, basically. What I'm saying is this is the HHV efficiency, right? That's how it's defined. If I multiply that by 1, which is the part on the right, now I've created a group. I can now take delta H of reaction at temperature T divided by delta H of reaction at 25C, and then I can break that as a separate term. And that leaves delta H of reaction at temperature T in the denominator. And that's relates to the thermoneutral voltage.
Okay, I understand. Thank you.